Welcome to all of you in lecture 4, Introduction of Thermodynamics. In the last class, we have discussed about pressure definition. As all of you know that pressure is defined as a force per unit area. We have already discussed some unit conversion of pressure. We already discussed about PSI unit, which is the most popular unit of pressure measurement in today's gauges. So by these conversion factor, we can convert PSI unit into SI unit. Okay, and it is very useful whenever you solve numerical problems. Right now, we talk about types of pressure. There are three types of pressure: absolute pressure, gauge pressure, and vacuum pressure. We can understand these types of pressure through this figure. I am trying to show you. Yes. Okay. Suppose this is a absolute pressure zero line. Okay. One by one, I will explain all types of pressure. Firstly, just assume that at this line, absolute pressure is zero. Later on, I will define what is absolute pressure. Okay. And another line is atmospheric pressure. And one more line that is representing gauge pressure. Okay. So here we can clearly see there are three types of line. First one, line first, representing absolute pressure value 0. Okay. Second one line representing atmospheric pressure. And third one line is showing gauge pressure. Okay. So if we assume this line as a reference line, okay, if we assume absolute pressure 0 line as a reference line, so whatever value of atmospheric pressure, whatever the value of atmospheric pressure that is showing, suppose we know in normal condition atmospheric pressure value is 760 mm, okay, of mercury. Okay, or we can say 101.325 kilopascal. We already discussed this unit kilopascal. That means kilonewton per meter square. That is atmospheric pressure value. So this atmospheric pressure value 101.325 kilopascal, that is with respect to absolute pressure 0 line. Okay. So that is the key factor, that if we want to, if we talk about atmospheric pressure value, that is always with respect to absolute pressure 0 line. That's value is 101.325 kilopascal. Okay. And if we consider atmospheric pressure as a basic, as a reference pressure, then this value is representing gauge pressure. Okay. If we take in absolute pressure 0 line as a reference line, then this is the difference is known as atmospheric pressure. And if we take in atmospheric pressure line as a reference line, then this difference is known as gauge pressure. Suppose I am taking an example. Okay. Anybody having, suppose pressure, absolute pressure 103.0 325 kilopascal. Okay, and if we want to show this pressure in this diagram, so we can clearly see from that point to that point, difference is known as 101.325 kilopascal, and this difference is known as 2 kilopascal. Okay, so if we define this pressure, if anyone ask that this body having okay absolute pressure 103.325 kilopascal, but what is gauge pressure of this body? So you can clearly see that gauge pressure, that means pressure of this body with respect to atmospheric pressure. Okay, and what is atmospheric pressure? That is 101.325 kilopascal. So we can clearly see that here gauge pressure of this body, P gauge, is defined as P absolute minus P atmospheric, and that's why P absolute of this body, that is 103.325 minus P atmospheric, that is 101.325, that is equal to 2.325 kilopascal. Okay, so this is the expression, important expression, that P gauge is defined as P absolute minus P18. Okay, so if we take in this absolute pressure line as a reference line, whatever be the total pressure, that is called absolute pressure. And if we take in atmospheric pressure line as a reference line, then pressure with respect to this atmospheric pressure line is known as gauge pressure. Okay, clear? Now we talk about vacuum pressure. What is vacuum pressure? Okay, so I just making some space to showing you, to explain about what is vacuum pressure. Okay, so see, if anybody having pressure below in compared to atmospheric pressure, if anybody having lesser pressure, lesser absolute pressure in compared to atmospheric pressure, then that body pressure is known as vacuum pressure. You can see, if anybody having suppose 5 kilopascal vacuum pressure, okay, anybody having 5 kilopascal vacuum pressure and asking about what is its absolute pressure, so you can representing this 5 kilopascal vacuum pressure in this manner. As I earlier told you that vacuum pressure is with respect to atmospheric pressure, and but difference between gauge pressure and vacuum pressure is that vacuum pressure is below from atmospheric pressure. Okay, so gauge pressure, we representing gauge pressure above of this atmospheric pressure line, but if we want to represent vacuum pressure, then we have to draw a line below of atmospheric pressure, because this vacuum pressure is lower in compared to atmospheric pressure. So this 5 kilopascal is representing that line. Okay, this representing 5 kilopascal, that is representing in a downward direction. Okay, so if we want to calculate absolute pressure of this body, so we have to calculate this value. So how we calculate this value? Simply P absolute, that is equal to P atmospheric minus P vacuum. Okay. So here, if this is 5 kilopascal, so we can easily calculate this value 101.325 minus 5, that is equal to minus that value, that is 96.325 kilopascal. That is P absolute value. So for vacuum pressure case, this is our expression. Okay. So now we again move towards our slide. Wait. So what is the definition of absolute pressure? Absolute pressure is defined as the actual pressure at a given position is called the absolute pressure, and it is measured relative to absolute vacuum, or we can say absolute zero pressure. Okay, as we shown in our figure, that absolute zero pressure line, that is the bottommost line of this figure. Another one, that is gauge pressure. Gauge pressure is defined as most pressure measuring devices, however, are calibrated to read zero in the atmosphere, and so they indicate the difference between the absolute pressure and local atmospheric pressure, because this gauge pressure is a lie above with respect to atmospheric pressure. That's why we can define this P gauge is equal to P absolute minus P atmospheric. Okay. And the last one, that is vacuum pressure. Vacuum pressure is defined pressure below atmospheric pressure are called vacuum pressure and are measured by vacuum gauges that indicate the difference between the atmospheric pressure and the absolute pressure. So P vacuum is defined as P atmospheric minus P absolute, or in our expression, I have defined this term like P absolute is equal to P atmospheric minus P vacuum. So same expression, both are same expression for vacuum pressure. So that's all about types of pressure. This is a figure which I already explained you. Now we take some numerical problem which is based on pressure measurement. Okay. So first problem is convert the following readings of pressure to kilopascal, assuming that barometer reads 760 mm of Hg. Barometer, that is the device which measuring atmospheric pressure value. Okay. So let us discuss this problem. Here three parts I have noted down. Problem. Yes. Okay. Here in problem, P barometer, that means P atmospheric, that is equal to 760 mm, and we have to convert all pressure readings into kilopascal. In the first part, problem is given 40 centimeter Hg vacuum. Okay. In second part, we have to convert 90 centimeter of Hg, that is gauge. And in third part, we have to calculate 1.2 meter of H2O gauge. Okay. So these are the parts of this problem. So I explain you one by one these parts. Okay. see that problem. So this is the problem. Firstly, we have to define pressure expansion. As all of we know that pressure is defined as force upon area. Okay, pressure is defined as force upon area. Okay, and force is defined as mg upon a. Okay, weight, that is a part of, that is a form of force. Okay, so P equals to mg upon a and mass equals to क्या होता है? Volume into density. So rho v g upon a. Okay, and volume is defined as product of area and height. So rho a h g upon a. That means pressure is defined as rho g h, where rho, that is the density, g, that is acceleration due to gravity, and h, that is the height of column. Okay, so in this problem, atmospheric pressure is given 760 mm of Hg. Okay, so what is that meaning 760 mm of Hg? Actually, in barometer, column of height of mercury, that is equal to 760 mm of Hg. Okay, so we have to calculate pressure value with respect to 760 mm of Hg column height. So by this expansion, we calculate atmospheric pressure value in SI unit. Okay, so P atmospheric, that is equal to density. Density of which substance? We are talking about 760 mm of Hg. So we have to consider value of density, that is density of mercury. Okay, so 13.6 into 10 to the power 3. That is the value of density of mercury, that is equal to 13.6 into 10 to the power 3 kg per meter cube. Okay, yeah, you have to mug up this. Okay, in lots of problem, you have to use this value. Okay, so mug up this value, density of mercury, that is equal to 13.6 into 10 to the power 3 kg per meter cube. So by using this expansion, that is PATM, density 13.6 into 10 to the power 3, G, that is 9.8 meter per second square, and H, what is H? 40, we are talking about measurement of atmospheric pressure. So 760 mm of Hg. So if we convert this 760 mm into meter, so what value? That is 0.76. Okay. So if we calculate this value, so this value is equal to 101.325 kilopascal. Okay, 101.325 kilopascal. Remember this. Here, density in terms of kg per meter cube. G, that is 9.8 meter per second square, and 0.76, that is in meter. So firstly, you will get atmospheric pressure value like that. That is 101.325 Newton per meter square or Pascal. So we can write like that 101.325 kilopascal. Okay, so you will get this atmospheric pressure value. Okay, but now we talk about 40 centimeter Hg vacuum conversion into kilopascal. Remember this, it is a value of vacuum pressure. Okay, so firstly draw last time figure, that is P absolute pressure zero line. Okay, this is the bottommost line. This is P atmospheric line. Okay, so if here this is a given 40 centimeter Hg of vacuum, that means this is 40 centimeter. If we convert into meter, then this is the value 40 by 1 centimeter, that is equal to 100. 1 meter equals to 100 centimeter. So we can convert this, that is 0.4 meter. Okay, this is a vacuum pressure line. Okay, this is a P vacuum, and we have to calculate this value. Convert the following degrees of pressure to kilopascal, assuming that barometer reads 760 mm of Hg. Okay, we have to simply convert into kilopascal. So in that case, if we want to convert this vacuum pressure into kilopascal just only, then simply what is that expression? P vacuum, that is equal to rho g h. That means rho, that is density of mercury, 13.6 into 10 power 3, g, that is 9.8, and h, that is 0.4. So if you solve this problem, then you will get 53.31 into 10 to the power 3 Newton per meter square. Okay, or in other words, you can say that is 53.31 kilopascal. Okay, I add one more step in this problem. If we want to calculate absolute pressure of this substance which having 40 centimeter Hg vacuum, then what will we do? See, I remove this part. Okay, so problem is that if we want to calculate absolute pressure with respect to 40 centimeter Hg vacuum, then what is the expression? This is the absolute pressure which we have to calculate. Okay, so what is this? This is atmospheric pressure, P atm. P atm minus P vacuum, that is equal to P absolute pressure of with respect to this vacuum. So P absolute, that is equal to P atmospheric minus P vacuum. Okay, as I told you in last slide that vacuum pressure is representing below the atmospheric pressure line. Okay, so if you want to calculate atmospheric pressure with respect to vacuum pressure, then you have to separate this vacuum pressure value with atmospheric pressure value. So simply the expression for vacuum pressure absolute pressure, that is P absolute equals to P atmospheric minus P vacuum. So atmospheric pressure is given as 101.325 kilopascal minus vacuum pressure value, that is 53.31. Then simply you will get the final value, that is equal to 48 kilopascal. Okay, so in this problem, firstly I have converted this 40 centimeter Hg vacuum into kilopascal, and then I have calculated absolute pressure value with respect to this vacuum pressure value. Okay, hope so. Now you can easily understand this concept. Now we move second part of this problem. In the second part, this is given that we have to calculate 90 centimeter Hg gauge pressure into kilopascal value. Okay, so simply, firstly you have convert this 90 centimeter Hg of gauge into kilopascal. So what will you do? Again, you apply this expression P gauge equals to rho gh simply. Okay, here this is again with respect to Hg, that means mercury. Again you adopt 13.6 into 10 to the power 3 into 9.8 into H. What is H value? That is 90 centimeter. 90 centimeter, you have to calculate this centimeter into meter. Okay, so this is that value is 0.9. When you calculate this value, this is equal to 120 into 10 to the power 3 Newton per meter square, or you can say that is equal to 120 kilopascal. Okay, again, if you want to calculate absolute pressure value with respect to this gauge pressure 90 centimeter of Hg, then again draw that is P absolute pressure 0 line. This is a reference line. Okay, I think this is not showing on board. Okay, I draw these lines in this portion. By this you can easily see this is the P absolute pressure line. Okay, P absolute pressure line, and this is the P gauge, or you can say this is the atmospheric pressure line. P atmospheric pressure line, and this is the P gauge, like that. Okay, so here P gauge value is 120 kilopascal. That means this value is 120 kilopascal. And in previous part, we have already calculated atmospheric pressure value. That is equal to 101.325 kilopascal. So we want to calculate this pressure with respect to absolute pressure. Okay, since we want to calculate absolute pressure, so what we do? We have to calculate this value. So what is this value? This is P absolute, that is equal to P gauge plus P atmospheric. Okay, P gauge plus P atmospheric. So P gauge, that is 120 plus 101.325. So value is that is equal to 221.325 kilopascal. Okay, so this is the value, absolute pressure value with respect to 90 centimeter of Hg gauge pressure. Okay, now we move for third part. What is third part? We have to calculate, firstly we have to convert 1.2 meter of H2O gauge pressure into kilopascal. Okay, so again we use this expression like first part and second part, that is P equals to rho gh. But now in this part 1.2 meter is given with respect to H2O. Okay, so we have to consider density of this part, that is density of water is taken for calculation. Okay, so here 1.2 meter of H2O gas, that means density of water we have to consider, that is 1000 kg per meter cube. Density of water, as all of we know, that value is 1000 kg per meter cube. So 1000 multiplied by 9.8 multiplied by 1.2. So this value is equal to 11.772 kilopascal. Okay, so this is the value of 1.2 meter of H2O water pressure value in kilopascal. Okay, and if we want to calculate absolute pressure value with respect to this pressure, this gauge pressure, then again we apply P absolute, that is equal to P gauge plus P atmosphere. So here 11.772 plus P atmosphere, that is equal to 101.325. So by adding, simply adding, you will get absolute pressure value with respect to this 1.2 meter of H2O gas pressure. So that is all about this first problem. Now we move in second problem. Okay, so firstly we see what is second problem. Wait, I am trying to show you. Okay, this is our second problem. Assume that the pressure P and specific volume V of the atmosphere are related according to the equation PV to the power 1.4 equals to 2.5 into 10 power 5. Okay, where P is in Newton per meter square absolute and V is in meter cube per kg. The acceleration due to gravity is a constant at 9.81 meter per second square. What is the depth of atmosphere necessary to produce a pressure of 1.033 bar at the Earth's surface? Consider atmosphere as a fluid column. Okay, so this is the problem. Firstly, we have to draw a figure to understand this problem. Okay, so firstly I am drawing figure of that problem. So see figure of that problem. Suppose this is a Earth surface. Okay, this is a Earth surface. Okay, and there are some atmosphere layers above the Earth's surface. As all of we know that if we move from Earth's surface to space, towards the space, then atmosphere layer will goes lesser and a lesser density as we move in upward direction from Earth's surface to space. Okay, so I am drawing these atmosphere layers. Okay, so suppose here this is the pressure P, atmospheric pressure. Okay, and this is the density. Suppose I consider a small part dh high in between the atmospheric layers. Okay, and this is the bottommost point. Okay, this is the weight W, and that is the weight of atmosphere layer. Okay, so that's all the word problem. Again, I'm repeating this problem, and I'm trying to explain this problem again with the help of this figure. Okay, so what is problem? The pressure and specific volume of atmosphere. Pressure of this atmosphere, okay, and specific volume of atmosphere are related according to equation. What is equation? That is PV to the power 1.4 is equal to 2.5 into 10 to the power 5. Okay, this is the equation. Pressure of this atmosphere layer and specific volume of this atmosphere layer are related with this expression PV to the power 1.4 equals to 2.5 into 10 to the power 5. Okay, where P is in Newton per meter square. Okay, what is P unit? That is Newton per meter square, and specific volume unit, that is meter cube per kg. Okay, this is. So question is that what depth of atmosphere is required to produce a pressure of 1.033 bar at the Earth's surface? What depth of atmosphere is required to produce a pressure? What is pressure value? That is 1.033 bar. Okay, so question asking about height of this atmosphere layer, which incident pressure on Earth's surface, that is 1.033 bar. Okay, so as we move in upward direction, so weight is also increasing of this atmosphere layer. Okay, so at what height this atmosphere is situated, what till height that create pressure value on Earth's surface, that is 1.033 bar. So we have to calculate that height. Okay, we have to calculate that height, which offering pressure value 1.033 bar on the Earth's surface. Okay, so as all of you know that 1 bar equals to 10 to the power 5 Pascal, or you can say 1 bar that is equal to 10 to the power 2 kilopascal. Okay, so we convert this pressure, that is equal to 1.0033 into 10 to the power 5 Pascal. Okay, so that's all about it. Now we focus towards this small element. Okay, this is small element which having dh height in intermediate state between Earth's surface and space. Okay, so at our point there is a pressure P, and due to this dh height there is something pressure dP. So that's why if we want to calculate pressure on that point, then pressure value is P plus dP. So net pressure which is acting at that point, that is equal to P plus dP. dP, that is pressure due to dh height. Okay, so simply you can say dP is defined as rho g dh. Okay, so if we want to explain this expression, that is AP plus dP, that is equal to mg plus PA. How we will get this expression? See that force is defined as product of pressure and cross-sectional area. Okay, force is defined as F equals to P multiplied by A. So if we draw free body diagram of this siege vent, the atmospheric pressure siege vent, then what we will see that force at this layer, that is pressure P plus dP multiplied by A. Okay, this is the force on that layer. That is equal to that force. That force is defined as P multiply A plus weight of this element. Okay, so and this weight, that is equal to M into G. Simply, the force which is acting in upward the force which is acting topmost layer of this atmosphere layer, that is equal to P multiply A plus weight that is acting in downward direction, that is equal to mg, is equal to pressure force which is offering at bottommost layer of this atmosphere layer, that is equal to P plus dP multiplied by A. Okay, so PA plus dP multiply A, that is equal to mg plus PA. So this is cancelled out. So we can simply see that dP. So in this problem, here we are getting dPA, that is equal to rho ADH multiplied by G. Okay. So here we simply cancel out this A term and we get term that is dH equals to, this G term is coming here, that is 1 upon G and 1 upon rho, that is equal to multiplied by dP. Okay, so here we are getting this term. Now when we solve this problem, this 1 upon rho is equal to specific volume V, small v. Okay, this 1 upon rho, that is equal to specific volume small v. So we get, that is 1 upon G dP small v, that is equal to dH. Okay, now if we divide with pressure P and multiply with pressure P, then consider this and this term P multiplied by V. In a problem we get PV to the power 1.4 is equal to 2.5 into 10 to the power 5. Okay, so by this expression we simply write this term that P, I write here, that is dH equals to integration of 0 to 1.033 into 10 to the power 5 1 upon G 2.5 into 10 to the power 5 upon P whole power 1 upon 1.4 dP. How we get this expansion? See, since here PV to the power 1.4 it is equal to 2.5 into 10 to the power 5. So in place of this V, we simply write this term, that is V equals to 2.5 into 10 to the power 5 upon P whole power 1 upon 1.4. By this expansion we can put this expansion in place of V and we get this term. Okay, so this is all about value of dH, and here we put this limit 0 to 1.0033 into 10 to the power 5 because we want to get height of that column, height of that atmosphere layer on which pressure is offering value 1.033 bar. That means 1.033 into 10 to the power 5 Pascal. That's why we put this limit 0 to 1.033 into 10 to the power 5. Okay. So by integrating this term, we get final value of H that is equal to 69.462 kilometer. Okay. Finally, we will get this value. I write this value at up. That is, final answer is H equals to, by solving this integration, we will get value of a small h that is equal to 69,462 meter. Okay, so this is the problem of atmosphere layer. Now we move towards our third problem. Okay, so what is our third problem? Share screen. So our third problem is that the acceleration of gravity is given as a function of elevation above sea level by small g equals to 980.6 minus 3.086 into 10 to the power minus 6h, where g is in centimeter per second square and h is in centimeter. If an aeroplane weighing 9,000 Newton at the sea level, what is the gravity force upon it at 10,000 meter elevation? What is the percentage difference from the sea level weight? Okay, so firstly we write values of g and other terms which is given in problem. So firstly we write terms value, see that here value of small g is given 980.6 minus 3.086 into 10 to the power minus 6h. Okay, this is the value. Okay, so in a problem, question asking that yes, the acceleration of gravity is given as a function of elevation above sea level is by g equals to 980.6 minus 3.086 into 10 to the power minus 6h, where g in centimeter per second square, that is in centimeter per second square, and h is in centimeter. This h is in centimeter. If aeroplane weight 90,000 Newton at sea level, weight of aeroplane at sea level, that is 90,000 Newton. So what is the gravity force acting upon it at 10,000 meter elevation? What is the gravity force? That means asking again weight of that aeroplane at height of 10,000 meter. Okay. That is the question. Okay. And again asking about what is the percentage difference from the sea level weight. Okay. In a final, you have to calculate percentage difference. Okay. So as all of we know that weight is defined as m into g. Okay. So in a first way, you have to calculate what is the mass of that aeroplane. Okay. You have to firstly calculate this value. What is the mass of that aeroplane? Okay. So see that weight is defined as m into g. So we consider weight of this plane at sea level, because we know that mass of that plane will not change. Mass is always conserved. Doesn't matter this plane is lie at the sea level or it will fly at the height of 10,000 meter. Okay, weight can be changed, but mass is always conserved. Okay, so firstly we calculate value of mass of this plane. Okay, so weight at sea level is given as 90,000 at sea level, that is equal to m multiplied by g at sea level. So in a problem, g at sea level is given as 9.81. Okay, at sea level g is given as 9.806. Okay, this is given g at sea level. This is a default value of acceleration due to gravity, 9.806 meter per second square. Okay, so by this we can calculate mass of that plane, that is equal to 9178.054. Okay, this is the mass of that plane. Clear? Okay, now we move towards calculating weight of that plane on the height of 10,000 meter. Since in a problem this is given that g is varying with respect to height, that means acceleration due to gravity small g, it is the function of elevation height, then we have to calculate value of this small g at the height of 10,000 meter. Okay, so we calculate this value g at 10,000 meter. Remember always which type of unit using this expression. Okay, here value of g when you will get finally, that will lie in the centimeter per second square. Okay, so remember this term. So 980.6 minus 3.086 into 10 to the power minus 6 multiplied by h. But we have to use this h value that must be lie in centimeter. Okay, so in a problem it is given that a plane is flying at the height of 10,000 meter. So before putting value of height in this expression, we have to convert 10,000 meter into centimeter. Okay, so here 10,000 meter multiplied by 1 meter, that is equal to 100 centimeter. So here we convert this value into centimeter. Okay, since 1 meter, that is equal to 100 centimeter. So we calculate and we get value of g, that is equal to 977.514 centimeter per second square. Okay, This is the value of G at 10,000 meter. Okay. Now, if we convert this G in terms of SI unit, then 9.77514 meter per second square. Okay. Since in 1 centimeter, 10 to the power minus 2 meter. So we have to divide this term with 100. Okay. And then this value is converted into meter per second square. Okay. So we get this G value at 10,000 meter. Now simply calculate weight of that plane at 10,000 meter. That is equal to mass that is conserved, but which G value at 10,000 meter. Okay. So value of mass is given, that is 9178.05, 9178.054 multiplied by 9.77514. Okay. So this is all about that is mass multiplied by G. Okay, you cannot see value of G. I write this G value here. That is 9.77514. Okay, now you can see. So finally, we will get weight of this block at height of 10,000 meter, that is equal to weight of that block, weight 10,000 meter. By solving this product, we get weight that is equal to 89716.765 Newton. Okay, so we can get final that weight on the height of 10,000 meter. And if we want to calculate percentage change of weight from sea level to at elevation of 10,000 meter, then simply percentage change calculated, percentage change of weight, that is equal to weight at sea level minus weight at 10,000 meter upon weight at sea level. Okay, so you will get final percentage change. Okay, so this is all about that is equal to 0.3147%. Okay, you will get this final expression. That is question number 3rd. Okay, so we will calculate some more problems in tutorial class. Okay, and after that we will discuss new chapter, zeroth law of thermodynamics. Okay, thank you very much.